Alrighty, welcome back, mathematicians. Today we are moving on to section 2.6 on limits involving infinity, asymptotes of a graph. So the last few chapters we've been talking about limits as x approaches some c. It'd be 0 on one side, 0 on the other side, or just some other actual number. So what about as x approaches infinity? Can we just plug in infinity? Infinity isn't a real number. So we say that we can never touch infinity, right? It's not like a number I can just go on the number line and oh, there it is. So we have to do something a little bit different. Well, then what does it mean for us to talk about the limit as x approaches to infinity of f of x? Just how we talked about, we wanted to, limits were about the behavior of the graph around a number. If we're going towards a certain number. Limits as we go to infinity, limits as x goes to infinity means we want to describe the end nature of a function, or as x is going off until forever. All right, so let's kind of do a little bit of an example. So we'll do the function 1 over x, one of our favorites. So I learned how to make straight lines. Amazing, right? So we know this function looks a little like this. Whoopsies. Right, so the limit as x approaches infinity of 1 over x, we can see that this is just going off and getting smaller and smaller and smaller and is approaching 0. And I know smaller, you might think of a negative number, but here we mean small in an absolute value wise situation where we're getting close to 0. What if we go to the other infinity, negative infinity? We can see that that's approaching 0 as well, but from the negative side. very small. So we could say that equals -0, but really that just equals 0. So we can define these two types of limits. So we say that the function f of x has a limit L as x approaches infinity and write similarly for as x approaches negative infinity. Alrighty? So a really important question is, do these limits, do they work the same way as, let's say if I was going towards 1 or as x was approaching 0? So they actually kind of do. They still follow those limit laws. So theorem 2.6.1, we could say all limit laws, right? Product, addition, subtraction, constant, multiple. So you can go back and look at those limit laws, and we define them as the limit as x approaches c, and you can just put in a limit as x approaches infinity, and all the laws hold, and if you put them with a negative infinity. All right, so let's do a few examples. And we're actually going to use the fact that the limit as x approaches infinity of 1 over x goes to 0 a lot. So keep that in mind. So our first example, we're asked to find the limit as x goes to negative infinity of pi times the square root of 3 over x squared. So we're going to use limit laws that say the limit of two functions or even three functions multiplied by each other is the limit of each of those functions. So we can rewrite as x goes to negative infinity of pi square root of 3 x squared is equal to the limit as x goes to negative infinity of pi over 3 times 1 over x times 1 over x. So those are my three functions. I know a constant always just the limit is that of that is always going to go to that constant. So this first function is going to give me pi over 3. Remember, pi is just a number. Times 1 over x, I know goes to 0. And 0 again. Which gives me a grand total of 0. Okay? So we use the product rule limit law for that one. Well, we also had a fun limit law that dealt with rational functions. Remember, rational or quotient functions is a polynomial divided by another polynomial or a function divided by another function. Can we apply that, the top divided by the bottom? So we'll do the limit as x approaches 5x squared plus 8x divided by 3 over 3x squared plus 2. Well, if I plug infinity in for all of those like I would normally if it was any number, I'd get infinity plus infinity minus 3. Well, that's going to give me a big number time plus a big number is still a big number. So infinity. And the bottom again will give me infinity plus another number, which is still infinity. What? Infinity over infinity? That doesn't make sense. It actually doesn't equal that. So what we're actually going to do, since infinity divided by infinity is, I think it's called improper, I believe is the correct term. But you just really, it's not, I say it's illegal. Don't do that. Don't write that. So what we're going to do is we are going to divide the numerator and the denominator by the largest power in the denominator. And I'll show you how this doesn't change the outcome of the limit. We're just kind of rewriting it as like multiplying by a fancy one, something over itself. All right, so the highest power of the rational function we have above is what? Right, remember the denominator is just 3x squared plus 2. So x squared is the highest denominator. Not the highest power in the denominator, right? It's your variable to the biggest exponent. Biggest, in this case, also implies positive and negative, right? X squared is a higher power than x to the negative 100, okay? So remember that. Same goes for roots. X to the 1/2 is a higher power than x to the 1/7 because 1/2 is bigger than 1/7, okay? So we're going to I'm going to rewrite my limit as x approaches, we're going to infinity. 5x squared. Wow, what is this writing? There we go. And so what do we mean by dividing the numerator and the denominator by the largest power of the denominator is I'm going to multiply the numerator by 1 divided by x squared, because that's my highest power in the denominator. And I'm also going to multiply the denominator by 1 divided by x squared, right? Multiplying by the reciprocal is the same as division. And since I'm doing it the top and the bottom, I can think of this guy right here as a fancy 1. He's so fancy. All right, so I'm going to say equal to, because these things are equal. So 5x squared divided by x. I can take it to each term, just like I would if it was like a number. Wow, I love that straight line tool. All right, so now every term now is divided by x squared, which is what we wanted. So let's simplify. These x squareds are going to cancel out. X squared divided by x squared. 1 is going to be gone to the bottom, so this is going to be x to the first power in the denominator, and then these two guys are just going to stay. Alrighty, so we have equal to, I'll write it down here. Eight divided by x minus 3 divided by x squared divided by 3 plus 2 divided by x squared. All right, now this is the same limit as we started with before, right? All we did is multiply by a fancy 1 and simplify. I couldn't think of the word. So now I can plug in. I'm doing air quotes, you can't tell, but we know that as 1 over x goes into infinity, the limit is that goes, as x goes into infinity of 1 over x, that goes to 0. So this is just 8 times that. 8 times 0 is 0. And same with this one. So we'll do it one at a time. So 5 is just 5. That's going to go to 5. Plus the limit. We're going to write this down a little bit. I want to show this in full detail so you guys can see it the first time. No, wait, I don't want the limit right there. Right, so that 5 is a constant, so he's just 5 plus the limit of 8 times 1 over x. X is still going towards infinity, minus the limit as x goes to infinity of 3 times 1 over x squared, which we know is 1 over x times 1 over x, and it'll behave the same. 3 plus the limit as x goes to infinity of 2 times 1 over x squared. If I have 1 over, or even just a number over x to some positive power, so I have x over 1 over x, 1 over x squared, and so on, that limit as x goes to infinity or negative infinity is always going to go to 0. So this is 0. This goes to 0. This one goes to 0. All right, so then you're left with 5 plus 0 over 3 plus 0. Well, that simplifies to 5/3. Okay. I know that's pretty long, but I wanted to show like every step. All right, so we're not always just going to get a nice little number. So let's do another example. So find the limit as x approaches, let's do negative infinity, 11x plus 2 divided by 2x plus 11. So again, if we plug this in, we're going to get infinity over infinity. So we have to do the dividing by the denominator thing. So the highest power here is what? It's x cubed. Good job. So the limit as x goes to negative infinity of 11x plus 2 divided by 2x cubed plus 11. Hopefully with practice, this process gets a little faster for you. So I'm going to write still the limit as x goes to infinity, or excuse me, negative infinity. 11, oh, that was cray-cray. 11x divided by x cubed plus 2 over x cubed, 2x cubed divided by x cubed plus 11 over x cubed. We can simplify before taking the limit. Keep writing the wrong infinity. 11x squared, 11 over x squared plus 2x to the third divided by x to the third, 2 plus 11 x to the third. So just from what we saw last time, I know that this is going to 0, this is going to go to 0, and this is going to go to 0. So we'll have 0 plus 0 over 2 plus 0, which gives me a whopping whole 0. Alrighty? So we actually have a special name for limits as x goes to infinity and positive and negative infinity, if we're looking at a graph. So remember how in the graph the limit as x approaches infinity of 1 over x equals 0, and the limit as x approaches negative infinity of 1 over x also equals 0? And our graph kind of look like this. So this red line that I just drew, that's y equals 0, or actually the x-axis. So as you can see, and that's also where these limits are going. We call that the horizontal asymptote. Like horizon, you look out on the horizon, it goes this way, horizontal asymptote. Asymptote. Spell that wrong. There we go. So that's what we call a horizontal asymptote, and we can define that a little bit better. So the line y equals b, it has to be a line, you can't just tell me it's a number, is a horizontal asymptote of the graph of f of x if either, so either means one or the other or both, the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity equals b. So in our case above, both of them equaled 0, so y equals 0 is a horizontal asymptote. Here is a question for you guys. Is there a maximum of horizontal asymptotes a function can have? Not all functions have an asymptote, so we know that the minimum is 0, but what's the max number of horizontal asymptotes a function can have? I'll let you guys sit on that one for a while. Let's do another example. So we're going to find all horizontal asymptotes for f of x equal to x cubed minus 2 over the absolute value of x cubed plus 1. So let's do the limit as x approaches infinity first. Note as x approaches infinity, it's approaching positive infinity. So absolute value of x cubed is just going to equal x cubed because they're already positive numbers. So we can see that this limit as x approaches infinity of x cubed minus 2 over the absolute value of x cubed is just x cubed. And then that plus 1 doesn't change. All right, we'll do our same spiel as before. So we'll get the limit as x goes to infinity. Our highest power in the denominator is x cubed. So we'll get 1 minus 2 divided by x cubed over 1 plus 1 divided by x cubed. Going a little faster now. If you need to pause and work that through, by all means, please do. All right, and I take the limit as x goes to infinity, so I get 1 minus 0 over 1 plus 0, which just gives me 1. So we have one horizontal asymptote at 1. Y equals 1. Not at 1. Y equals 1. All right, so then we'll do the limit as x approaches infinity. X cubed minus 2, absolute value of x cubed plus 1. Note as x goes to negative infinity, all those numbers are negative, so I want absolute value makes numbers positive, so if those numbers all negative, absolute value of x cubed is going to be a negative x cubed. Because if I'm plugging in like a negative 100 into x, negative 100 times a negative will give me a positive number. So that's why that negative is in front of the x cubed. So equal to the limit as x approaches negative infinity of x cubed minus 2 over negative x cubed plus 1. Just equal the limit as x goes to negative infinity. We divided by x cubed again in the denominator and the numerator. And we'll get 1 minus 2 over x cubed, negative 1 plus 1 over x cubed. And so we'll get 1 minus 0 divided by negative 1 plus 0, which gives me a negative 1. So we can say that f of x equal to x cubed minus 2 over the absolute value of x cubed plus 1 has two horizontal asymptotes at y equals 1 and y equals negative 1. I'm going to show you guys a light sketch of this function because I also want to show you something interesting that happens. So our horizontal asymptotes, we can draw these right here at negative 1 and 1. Wow, I love this. This is so fun. Okay, so I drew a beautiful picture. So we're going to go. Right, and so that black line is our function. And the red lines are our horizontal asymptotes. So you can see right here that we actually intersected the horizontal asymptote. I thought asymptotes I learned in algebra that I couldn't cross. You can actually cross a horizontal asymptote. Usually the graph will, if it does cross a horizontal asymptote, it'll only cross it a finite number of times, so 1 or 2 times. But you can see that as x is approaching negative infinity, right? Those are all negative numbers. So 1 was for all those negative sorry, I wrote this upside down. Positive 1, negative 1. There we go. So at this point where it crosses, that's when x is a positive value. We made positive values. We made that assumption that those are all going to be under 1. The negative values are all going to be approaching negative 1. So a positive value of x crossing the horizontal asymptote, it kind of makes it a little bit okay that it's the horizontal asymptote as x goes to negative infinity. I hope that makes sense. So let's do a few more examples and then move on. Let's take a little bit of a break right now. Whoopsies. And then I'll come back. All right, we're back. I'm trying this new thing where I record for a little bit and then stop recording and then record again just to make sure that the video is like actually there after all these technical difficulties. So first example we're going to do is the limit as x approaches infinity of sine of 1 over x. So we learned last section in continuity that sine is a continuous function, and so we can move the limit on the inside. So when we do that, we get the following. Right, so we move the limit inside. We know as x goes to infinity, that goes to 0. So sine of 0, and then we know that equals 0. But there's another way, and there's another more useful way, even though in this case it kind of seems like duh, but in later examples you'll see why. So let's call theta 1 over x. So as x goes to infinity, theta goes where? Goes to 0 from the left or the right side? From the right side, positive, right? Because those numbers are never going to be negative. They're just going to get smaller and smaller positive numbers. So that's why it's 0 from the right side. So we can then rewrite our limit as x goes to infinity of sine of 1 over x. That's going to equal the limit as theta goes to 0 on the right-hand side of sine of theta. Whoa. Alrighty. Then we get sine of 0, and we all know that equals 0. Why did we do all that extra work to just get to the same spot? Well, let's show in our next example, 2, the limit as x approaches infinity of x sine of x. Wait, I want to show you guys an important notation. So whenever you see limit as x approaches plus or minus infinity, that means they're asking you to find the limit as x approaches infinity and the limit as it approaches negative infinity. That should be 1 over x. All right, I think that's show on your homework, so I just want you guys to get familiar with that notation. So first, let's do the limit as x goes to positive infinity. Well, I know that, well, as the limit as x goes into infinity of x times the limit as x goes to infinity of sine 1 over x. Well, won't that just give us infinity times 0? Well, is that 0? A small, any number times 0 is 0, but that's a really, really big number. Ooh, this actually isn't defined. It doesn't mean the function's not defined. Just infinity times 0 is not defined. So this is where theta equaling to 1 over x is very useful. As x goes to infinity, theta goes to 0 from the right-hand side, and as x goes to negative infinity, theta goes to 0 on the left-hand side. So, limit as x goes to infinity, x 1 over x, sine 1 over x, that's going to equal the limit as theta goes to 0 from the right-hand side of x is the same as, 1 over theta, because we defined theta to be 1 over x. I can rearrange that to be 1 over theta. So that makes that x times sine of 1 over x as sine theta over theta. What? This looks like my favorite limit. Awesome. So what I've kind of been drilling in your minds is that the limit as theta goes to 0 of sine of theta over theta is 1. Beautiful. Let's do it as x approaches negative infinity of x sine of 1 over x. It's the same limit as before. Theta is now approaching 0 from the left-hand side. And we still know that that equals 1. This does not mean that infinity times 0 is 1. That is not true. Infinity times 0 is not defined. So we've seen 0 times infinity. We saw infinity over infinity, I'm pretty sure. I forget where it was, but we saw it. What about 0 divided by infinity? Right? So what about the limit as x goes to infinity of sine of x over x? We know what it is going to 0, but what about infinity, right? I plug that in. And, well, sine of x doesn't go, it oscillates between 0 and 1. So, but x goes to infinity, so I don't really know. So let's see. We can actually still use sandwich theorem when we have limits dealing with infinity and negative infinity. How do we get our two sandwiches though? So I want you guys to see that we know sine of x is going to be between 1 and negative 1, right? So if I just divide everything by x, sine of x over x is bounded between negative 1 over x and 1 over x. So let's take the limits of our bread, which is x goes to infinity of negative 1 over x. Well, that's just going to be negative 0, which is 0. And the limit as x goes to infinity of 1 over x, we know that's 0 and 0. So we have that the limit of x approaching infinity of sine of x over x is bounded between 0 and 0. So the limit of x approaches infinity of sine of x over x should also equal 0. Yay! All right. So what about infinity minus infinity? Is that going to equal, like, which infinity is bigger? How do I figure that out? So when talking about limits, examples are the best way to do it. So we're going to find the limit as x approaches infinity of x minus the square root of x squared plus 16. If we plug in a big number, I'm going to get a big number minus another big number. So we're going to multiply by the conjugate. The conjugate of a number a plus a number b is a minus b. Note that the conjugate of just a number, let's call it a, is a, right? Because a is like a plus 0, so its conjugate would be a minus 0. That's just a. So the conjugate of x minus the square root of x squared plus 16, it's going to be x plus the square root of x plus 16. So this is A, and this is B. So I'm going to take the limit as x approaches infinity of x minus square root of x plus 16 times x plus square root of x squared plus 16, and divided again by the same thing, right? We love to multiply by a fancy one. Whoa, I don't need a big parenthesis there. Fancy one. So then, conjugates also have the property of sum of squares. If you're not familiar with sum of squares, I really suggest refreshing yourselves. We don't have time to go over them. But when I have a plus b times a minus b, I get a squared minus b squared. So that's going to be x squared minus the square root of x squared plus 16 squared over this hoopla on the bottom. So x squared minus 16, x minus, no, x plus, that's important. Woo! So I forgot something very important when writing this out. I forgot to include my limit. Those things are not equal without my limit right there. So don't forget your limit like I just did. Great, so now I have a rational function. I know how to deal with those, but what is my largest value in my, or sorry, highest power in my denominator? Is it x squared? It's actually x. Note that x is equal to the square root of x squared. So I can rewrite this as the limit as x goes to infinity of negative 16 divided by x over x divided by x plus x squared, the square root of x squared divided by x squared plus 16 divided by x squared. Okay? I'm dividing the ones in the radical by x squared because I'm technically multiplying it by the square root of x squared. So the limit as x goes to infinity of negative 16 over x, 1 plus the square root of 1 plus 16 over x squared. Right, as x goes to infinity, we know that that's going to equal 0 over 1 plus the square root of 1 plus 0. And that simplifies to 0. All right. All right, cool. Let's see if we can get one more example, and then I need to take another break because my pen is dying. So we're going to find the limit as x approaches infinity of 2x to the 5th minus 6x to the 4th plus 1 over 3x squared plus x, whoa, plus minus 7. And this is actually going to negative infinity. That's important. All right, and we're going to rewrite that limit after dividing by x squared So we'll get 2x divided by x third, no, squared, excuse me. Minus 6x to the fourth over x squared plus 1 over x squared. We can simplify. All right, so we get 3x cubed minus 6x to the fourth. Oh, wait, no, that should be a 2. X squared, excuse me. Plus 1 over x squared, all divided by 3 plus 1 over x minus 7 divided by x squared. Alrighty, so then we apply our limit, and we'll get 2x cubed. Cube means the negative, you'll have like negative infinity cubed, so that's going to equal negative infinity minus, I think that is minus a negative infinity cubed, an infinity plus 0 over 3 plus 0 plus 0. So why did I get to write infinity here where we haven't been able to before? It's kind of, I want to show you, we don't need this cubed right here. Infinity, if you want to think of it as just like a huge number, and especially a negative huge number. So 2x cubed, if x is a huge number, that's going to be a huge negative number. X is like a very large negative number. 2 multiplying or cubing it, going to make it a large negative number, and 2 is going to make it an even larger negative number. For 6x squared, that's a large negative number. Squared is going to be a positive negative number, and then I'm subtracting it. So I get infinity minus infinity. So a large number, a large negative number minus another large number will make it an even larger negative number. So I get negative infinity. So there's sometimes where infinity kind of works, right? I also know that I can multiply infinity by itself, a big number times a big number. So a negative infinity minus a negative infinity is going to give you a negative infinity. If I divide it by 3, that's still a large negative number, which we call infinity. I could have also rewritten this and gotten an infinity times a negative infinity. Well, a large number times another large number, still a really large number. So these two things are not really defined, but we can kind of justify them in our heads of why they're true. Also, I think infinity, a big number plus another big number, it's going to equal a big number. Alrighty. So take a break, and then we're going to talk about vertical asymptotes. Alrighty, so let's wrap this up. So remember we had limits that equal 0 as x approaches some number. So let's look at the graph f of x equaling 1 over x squared. So I thought I'd switch it up so we don't always look at 1 over x, but the same kind of thing applies. So we can see that the limit as x approaches 0 from the right-hand side of 1 over x squared, that is going to positive infinity. Same with the limit as x approaches 0 from the right-hand side of 1 over x squared. That's also going to equal infinity. So if I draw a line here, what do you think we can call this line? We're going to call that our vertical asymptote. So we also have a formal definition for that one. So a line x equals a, remember our horizontal asymptote was y equals b, so this is x equals a, is a vertical asymptote of the function f of x if either, not 8, the limit as x approaches a from the right of f of x equals plus or minus infinity, or the limit as x approaches a from the left of f of x equals plus or minus infinity. Okay? So if we're looking at a graph, usually vertical asymptotes are going to be where the denominator equals 0. That'll kind of be an indication of where we need to look. So let's look at this example. We're asked to find all vertical asymptotes of f of x equal to -8 over x squared minus 4. So note that x squared minus 4 is difference of squares, so we can factor that to be x plus 2 and x minus 2. And that all equals 0 when x equals 2 and x equals -2. So not always true when the denominator equals 0 is there going to be a vertical asymptote. You still need a test, right? There could be things in the numerator that cancels out, and there might not be an asymptote, but more like a hole, like have we seen in earlier chapters. So you still need to check them. So let's do the limit. Whoa, where did that 0 come from? So the limit as x approaches 2 from the right, so we are going to write x minus 2 and x plus 2 in the denominator. Product rule of limit says that we can separate these, and that is kind of what I find the easiest thing to do, so you can focus on what's going to make this go to infinity and what's not going to make this go towards infinity. So -8 divided by x plus 2, that's not, as x goes to 2, that's not going to go towards anything of significance, times the limit as x goes to 2 on the right-hand side, 1 over x minus 2. So if we plug in positive 2 into this first limit, I get negative 8 over 4, which is good. That's not going towards infinity. And then I get, so 2 from the positive side, that's going to give me numbers that are bigger than 2. So that's going to be positive infinity. So then this is going to be what, negative 2 times positive infinity. So that's negative infinity. That's why it's still important to look at that other bit. Even though this is going towards infinity, it's going towards negative infinity. If you tell me this is going towards infinity, that's a wrong answer. That negative is really important. Let's check the limit as x goes to 2 from the left-hand side. Oh, not 2 plus. So we have the same thing as before, we just now have an x minus x approaching 2 to the minus. So we're still going to get negative 8/4 times, so this is the limit as x is approaching 2 from numbers that are smaller than 2. So that's going to give me a negative infinity because it's a number smaller than 2 minus 2, so that's 1 over a really small negative number. So that's going to give me negative infinity, so this is then going towards infinity. All right, and then I continue with this on for x approaching negative 2. And then from there, I can see that both of these, x equals 2 and x equals negative 2, are vertical asymptotes. So we're probably looking something like something kind of like that. You can also go on and find horizontal asymptotes to even help you more to see what the graph looks like. This is kind of all foreshadowing of what we're going to be doing in the future and the more stuff we're going to learn about properties of functions. So let's do one last example and then we will be done with this lecture. We can move on to 3.1. So we want to find all the vertical asymptotes of secant of x. All right, so let's remember that secant of x is the same as 1 over cosine of x. So when is cosine of x equal to 0? So I also learned how to draw a circle. Nope. How did that turn into a line? Oh, look at that. Amazing. Okay, cool. So okay, cool. So the unit circle cosine is going to be 0 at pi over 2, 3 pi over 2, and then I can keep going around the circle. So I can then go again at 5 pi over 2, 7 pi over 2, and so on. So we can write this out. Every odd iteration of pi over 2. So we can also write this as 2n minus 1 pi over 2, where n is an integer. That's what that double bar z looks like. So that's just how you write all of the odd versions of pi over 2. And we can actually draw this graph. Because I think I know what it looks like. So we'll call these guys pi over 2. Also, knowing where these asymptotes are really helps you find the period of the trig function. Remember we talked about that in chapters 1.3? Okay, cool. I know what secant looks like. And you can see that there's, in fact, almost an infinite amount of vertical asymptotes. Okay, so that's all we have for this section. We're moving on to 1.3, not 1.3, 3.1. And we're kind of going to circle back to tangents and derivatives at a point, now using all the knowledge that we have before. All right.